All right, we're going to start chapter 18 today, but were there any questions from chapter 17?
What?
Chapter 17 questions or earlier? No. All right, chapter 18. We have two new K's we're going to deal with. There's something called KSP and KF. And so we'll look at KSP first. KSP, this is called the solubility product. So let's just redefine what solubility is. What is solubility? Well, there are two definitions for solubility. One is a kind of a qualitative definition. You know what the qualitative definition is? Will it dissolve in water? Yeah, that's it. You know what the cutoff is?
One mole.
Well, you know, we have three categories. And so when we're thinking about solubility, yeah, 0.1, that's good. You know, qualitative, the three categories are this. It's insoluble, which we give it an I. It's slightly soluble, which we abbreviate SS, or it's soluble, which we give it an S. And these qualitative definitions, this is from Chem 1A, you know, the solubility rules. And so we can put those in here, which means if it's insoluble, then less than 0.1 molar. In other words, less than 0.1 moles will dissolve per liter. 0.1 moles, actually, that seems like quite a lot, doesn't it? Yeah. And so the range of compounds, you have compounds that hit this edge here, you know, of 0.1 moles per liter, and it's fairly soluble. But then you have things that you can't even get a micromole in, or less. You know, things that are highly insoluble, like silver chloride. You know, silver chloride, how many moles can you dissolve in a liter? Anything? Well, it turns out a little bit will dissolve, but that little bit is just a tiny amount. And so over here we have greater than 0.1 molar, and here it's going to be about 0.1 molar. So those are our cutoffs. Quantitatively, you know, this is very broad. I mean, if something's insoluble, you don't know the extent of it. It could be highly insoluble or just a little bit insoluble. And so quantitatively, you know, solubility, which this might be confusing because we'll give the symbol S to solubility here. The solubility is equal to the max amount of solute that will dissolve in a given amount of solvent or solution. Oops. Okay, this is recording. And so typically what we do is let's look up some things like maybe something like calcium fluoride. We look at some data from calcium fluoride. Usually this is one of its physical properties here. You can see. Calcium fluoride, would you expect it to be soluble or insoluble in water? What about calcium chloride? Soluble or insoluble? Soluble. You know, chlorides, bromides, and iodides are all soluble except for silver, lead, and mercury. And so I'd expect calcium chloride to be soluble, calcium bromide, calcium iodide, and even calcium fluoride I would have expected it to be soluble because it's just another halide, right? But what would we call it? If you look at the solubility in water, and temperature is going to influence solubility here, so we give two temperatures here. 20 degrees C, we have 0.0016 grams per 100 milliliters. At 18 degrees C, 0.0015 grams per 100 milliliters. And so some of it dissolves. 1.6 milligrams dissolves in 100 milliliters at 20 degrees C. Is that very much, 1.6 milligrams? No, not very much. And so it's fairly insoluble. But we need to calculate the molarity to see where it falls in this category, right? You have to calculate the molarity. But most solubilities are grams per milliliter of solvent because this is easy. You take 100 milliliters of water and figure out how many grams you can dissolve in it. That's easy to do, right? And so most of the solubilities you're going to see are grams per milliliter of solvent, like this. But in this chapter, we aren't going to be dealing with these types of solubility. We're going to be doing molarity, in other words, the molar solubility. Molar solubility. How do I get from this to molar solubility? Well, I need the molar mass, right? Convert grams to moles. Is that it? And then convert milliliters to liters? And then I'm done? No. Because this is milliliters of water. Solvent. And so, you know what I need to do? I probably need to figure out how many grams of water I have. Well, how many grams of water is this? 100 grams. And then I'd have to figure out how many grams of solute I got in there. And that's the grams of solution if I would combine those two masses. And so if I know how many grams of solution I have, then I would just need to know the what? I'd need to know the density of the solution in order to get the molarity. And so going from here to molarities, we need density of the solution as well, as we can add up the total grams of solute and solvent, the mixture. Here's, we look at some other solvents like acetone, which is fairly polar, but mid-polarity, slightly soluble in acid. It's calcium fluoride. It's different than your typical halide.
If the amount of calcium chloride in water is so small, why can't we just assume the density is close to the density of water?
We could. We could do that. If it's very small, a milligram, 1.6 milligrams in 100 milliliters isn't much, But some things dissolve a lot more. And so if you were to automatically assume that each time you did a calculation like this, you'd be wrong some of the time.
Average.
But as long as you justify it, then you're okay. You'd say something like this would lead to what kind of error? Maybe like a 1-2% error. It's all right. As long as you're willing to accept that. If you want a more precise number, more accurate number, then you wouldn't do that.
So what makes calcium fluoride an unusual halide?
Yeah, that's a good question. Why is that? Why is chloride, bromide, and iodide kind of similar in certain ways, but fluoride's a little different? What would you think? It's related to its size.
The size of fluorine?
The size of fluorine, right? Fluoride. The size would be the first thing we'd look at, and then you'd look at the how it is. Does it follow a trend like calcium chloride? Even though we call it soluble, is borderline. Does it follow a smooth trend, or is fluoride a outlier? If it's an outlier, then it's probably not the size because the size varies smoothly, right? Iodide, chloride, fluoride, something like that. So if it's unusually large or unusually small, then we would look for other factors, and it would have to do with the bonding, because in order to get it into water, you have to break the bond. And so it could be that there's more covalent interaction in the bond, which would make it more difficult to break in solution, something like that. And so that's the first thing. But we look at the data and let the data tell us, because the data is experimental fact. We can come up with some kind of theories. But oftentimes you think about these theories, and these theories are what they call ad hoc. Have you ever heard ad hoc? Ad hoc is after the fact explanation. It's easy to explain things after the fact because then you say, oh, it's because of this interaction or that interaction. But to predict it, before the fact, that's what we want to do. Well, anyway, let's continue on here. Here's some nice crystals of silver chloride here, but the color looks off, doesn't it? What color is that? Silver chloride is what color? White. Well, anyway, I just wanted to look at the solubility. Now, we look at calcium. Calcium fluoride we call insoluble, and silver chloride we call insoluble. But take a look at the solubility of silver chloride, 520 micrograms. Well, 520 micrograms is only 0.5. It's not that different. 0.5 milligrams, right, per 100 milliliters versus 1.6 milligrams. And so it looks like calcium fluoride is, about 3 times more soluble. But both of them you can't get that much in water. And so the solubility is important because the solubility is going to tell us, what is the max amount I can get, not just some kind of qualitative estimate of it. And so in this chapter, we're going to be looking at calculating things like solubility.
Would the solubility adjust like other equations where, like, if you use the ions in solution, the solubility will take more of the solid and put it into... Yeah.
If all we were doing is calculating simple solubility, that is, how many grams of this crystal will dissolve, these crystals will dissolve in water, then there's not much to this particular chapter. But what we're looking at is we're looking at all the ways we can manipulate solubility. And you've already done these. How did you manipulate solubility? You manipulated solubility, for example, with your synthesis. How did you do that? Decreased temperature, right? Decreased temperature can do that. And so what we want to do in this chapter is we just don't want to say, well, if you decrease the temperature, it should become less soluble. We want to do, if you decrease the temperature, what is the new solubility? Let's calculate it. Or other things, like what? You change the solvent and things like this. What I failed to tell you is, when you're trying to precipitate out silver chloride, right? You saw this in lab yesterday. If you're trying to maximize the amount of light blue precipitate, will you just keep adding drop after drop of ammonia? Because what happened eventually? The precipitate disappeared. And so what happens is you add the ammonia and the precipitate increases and reaches a maximum, and then you keep adding the ammonia and the precipitate decreases and eventually completely disappears because you're destroying the precipitate. So in that way we're manipulating the solubility. We want to minimize the solubility, and then all of a sudden we're increasing the solubility. Well, the same thing happens in your unknown analysis. I told you, okay, you just keep adding the chloride, right, HCl. But there's a danger to adding too much chloride because of this. The precipitate can actually disappear. And so normally when you're doing precipitations, you watch it carefully. You watch it carefully and you want to maximize the amount of precipitation. That's always the case. And then if you keep adding and you start seeing the precipitate disappearing, you better stop. This complex here, the dichloro argentate 1 ion, isn't too big of a risk here versus the tetramine copper 2 complex is a big risk. That one is very stable. This one, you're probably pretty safe even if you overshoot it quite a lot. You probably need very, very high concentrations of chloride actually make that precipitate disappear, you probably couldn't make it disappear. You know, you couldn't get the chloride concentration high enough to make it disappear because this isn't as favorable. However, you know, we could use other agents to dissolve. For example, ammonia worked fabulously for dissolving silver chloride, right? You just add ammonia and attack the silver chloride precipitate and form the diamines, silver ion, like silver 1. Thiosulfate is a very common ligand that's used. It's also a reducing. Is it reducing? Well, no. Sulfite is a pretty good reducer. Thiosulfate here, well, this is good, but this is a pretty good ligand here, and can dissolve that as well. And so in this chapter, we're looking at different ways that the solubility can be manipulated. Silver chloride is light sensitive. This is a photochemical reaction, it's a redox reaction. And what you're doing is you're just oxidizing the chloride and reducing the silver from silver metal, chlorine gas. All right, the solubility product, let's take a look at that. KSP for silver chloride in water is 1.77 times 10 to the minus 10 at room temperature, which indicates that only 1.9 milligrams of silver chloride will dissolve. And so what the KSP is it's this. Yeah, pH influences, you know, we'll see different factors, and we're going to look at all the factors that influence solubility. You know, but let's take a look at the KSP equation first. You know, the KSP equation for something like silver chloride looks like this. Silver chloride solid goes to silver ions plus chloride ions. And so if we look in the forward direction, this is the dissolution or dissolving reaction. And if we look at the reverse, this is the precipitation or crystallization reaction. Okay. And so it's always written this way, you know, dissolution of forward. So we always start off with a solid. It's never written in the reverse. You know, even if you're doing a precipitation, we always write it like this. We always write the equation the same way each time. And so if we're doing a precipitation, it's going this way, right? If we're doing dissolution, it's going this way. And so normally with dissolution, we get plus S molar plus S molar. This is dissolution. You know, if it goes forward. And so in other words, we're dissolving it, and it's going to stop, it's going to reach equilibrium. And when it reaches equilibrium, it reaches its solubility. Because when we think about this, this is why we use S here. Because S molar is equal to the concentration of the silver ion, which is equal to the concentration of chloride ion, which is equal to the concentration of silver chloride that dissolves. Because it's all 1-to-1 mole ratio. And so it's going to be, in other words, this is called the solubility of silver chloride. You know, the amount that can dissolve here. Versus the reverse direction. If we go in the reverse direction, then we're losing minus X molar. In other words, we're getting precipitation occurring, so we're losing some of the product to form a solid. And so let's do a simple one here. We can go from S to KSP, or we can go from KSP to S. Okay. And so if we go from S to KSP, then what we need is the molar solubilities for this. And and figure that out. The way we do this is here. We set up an ice table with the KSP equation. And the ice table is going to just, you write out the KSP equation. Initial silver chloride we ignore. Initial we say nothing's dissolved. Then we add, in other words, some silver ions and chloride ions as the silver chloride starts to dissolve, and then it'll reach its maximum, that is saturated solution. Saturated solution, we're going to get the S. And then we have the KSP is equal to the silver ion concentration and the chloride ion concentration, which is just S times S, which is just S squared. So if we know what KSP is, we can solve for S, or if we know what S is, we can solve for KSP. Typically, we know what KSP is because we're going to have big tables of KSP numbers. And so most of the calculations you're going to be doing will be taking KSP and figuring out what S is, the solubility. All right. Now, salts can get more complicated. For example, calcium fluoride. Calcium fluoride solid would go to what? Calcium 2 plus 2 fluoride. Here. It would go to calcium 2 plus 2 fluoride, assuming what? Complete, not complete dissolving. It's not going to completely dissolve. You know, a little bit will dissolve, right? 1.6 milligrams will dissolve in 100 milliliters. That little bit that dissolves, we're assuming that that little bit that dissolves does what? Well, it's got to dissolve stoichiometrically, otherwise we're going to lose atoms or create atoms out of thin air, or into thin air. So it's got to dissolve stoichiometrically. But you're close. What would you say? Assuming that
Can you repeat the question?
it's going to form this, assuming what? No, it's not very soluble. We call it insoluble. It's insoluble, but a little bit will dissolve. And so we care about that little bit that dissolves. In fact, KSP we don't usually do for things that are soluble. In fact, in this chapter, we're always looking at insoluble species, because if we did things that were soluble, what would happen? Well, the concentrations would be large.
It'd be like,
so what?
It'd be like what we do with strong acids for KSP. Yeah, KSP is very good.
No, K is not very big. Unfortunately, KSP is not very big for this.
No, for very soluble.
Yeah, oh yeah. No, it's not though. It's not infinitely soluble. If we did K is very big, right? Let's say I had 1 billion grams of salt and 100 milliliters of water. K is very big, right? So I expect all of it to dissolve. Will all of it dissolve? No. Certain things are miscible. Do you guys know miscible? What does miscible mean? It's infinitely soluble. So some things are infinitely soluble, but most salts have a limit. Even sodium chloride. Sodium chloride is highly soluble, but you can only put like 36 grams in 100 milliliters. That's not infinite grams, right? And so even sodium chloride, which is highly soluble, has a limit. And so we could call that limit S, right? But I'm starting to deviate from the point of all this. The point of all this was we can assume that it splits up nicely like this.
It doesn't react with anything. Well, it doesn't react.
Assuming both of the fluorides break off? Yeah. Actually, think back to chapter 12. 12 or 13. Chapter 12 or chapter 13. Think. Actually, we don't have time to think. Let's just do this. It would do this if we assume that it behaves ideally.
For the activity.
Right? It behaves that there's no ion pairing, that the fluorides break off cleanly, you know? Because if there's ion pairing, then we're going to have other species in here, which is going to complicate this. And so for our calculations, we assume ideal behavior. And so it's just going to break apart completely. Now, is that accurate? No. And so these calculations, you know, if I was going to compare, you know, silver chloride maybe with this, or, you know, or if I were to make a comparison, I'd say maybe the higher charge, the bigger the error in assuming that. Maybe the lower charge, the smaller the error. So, you know, this is just like using the ideal gas law. You know, we're assuming ideal behavior. So if we start to deviate significantly from ideal behavior, then we know we're going to introduce or be introducing error into our calculations. Okay. But anyway, if we keep it simple like this, then, you know, the setup is easy. We start off with nothing dissolved, and then there's a change. So the change is going to be what? Plus S plus 2S. And so we're going to have S and 2S molar, where S, you know, it's a 1-to-1 here. And so the moles of calcium that dissolve per liter is the same as the moles of calcium fluoride that dissolve per liter. And so S is the solubility of calcium fluoride. How many moles of calcium fluoride we can get to dissolve in a liter? And so here the KSP is equal to the calcium concentration times the fluoride concentration squared, which is going to be S times 2S squared, which is going to give us 4S cubed. And so the solubility is different. You know, over here, to get the solubility, we just took the square root, right? Because S squared is equal to the KSP. If you want to figure out what S is, take the square root of the KSP. That's exactly what they did here. Over here, we're going to have to take the cube root, divided by 4. Divide by 4 first, and then take the cube root, etc. And so these are the KSP type, and we're just going to assume ideal behavior. It's just going to make our life a bit easier. All right, what's one way to decrease the solubility? Actually, what do you think? Do you need to do a calculation like this, or it seems pretty straightforward to calculate S or KSP? Straightforward, okay. What are some ways of decreasing the solubility? Lower the temperature. That's one way. We'll talk about temperature and K in the latter chapter. We'll do some calculations. It's going to come later. What's another way to decrease the solubility? I'm sorry? Change the solvent? Okay. Changing the solvent we aren't going to do. Everything in this chapter is going to be water. Sometimes we could change the pH. That might do it. In this case, it doesn't at least directly look like it's going to do it. Another way to do it is by doing this. And so we'll look at the next section, which is called the common ion effect. The common ion effect will decrease the solubility because, let's say, if I have calcium fluoride solid here, I got calcium 2 plus 2 fluorides. If I have some initial concentration of fluoride in here from somewhere else, and this is 0 molar here, and so maybe I add some sodium fluoride to this, let's say, from sodium fluoride. And so I have some fluoride from sodium fluoride here. Am I going to get as much to dissolve? No, I'm still going to have a change. The change is going to be plus S plus 2S. And so at equilibrium, I'm going to get S molar, and then the initial concentration of fluoride plus 2S molar. And so here, S has got to be smaller. And it's still equal to the same K. And so the more fluoride I put in there, the lower the solubility. And so this is how precipitation works. You know, in precipitation, what do you want to do? If I want to precipitate out all my calcium, you know, is that possible? I want to, you know what? I want to precipitate out 100%. Folks, I need to set up a precipitation. Let's set up a precipitation. So let's say I have some calcium in here, initial. Let's say there's 0.100 molar calcium. In precipitation. How much fluoride would I have to add to precipitate out 100% of my calcium?
You dissolve out your precipitate.
I want to precipitate that out. Okay, let me set it up in the ice table. Maybe that'll be easier to see. So here I have you know, for precipitations I set up the equation the same even though it's going backward. And so I have some calcium in here initial, and let's say I have 0 molar fluoride. And the calcium's from something like calcium nitrate. Let's say this is from calcium nitrate. So we got some calcium nitrate. I want to, you know what I want to do? I want to add some fluoride and precipitate out my calcium. How much fluoride do I need to add to precipitate out 100% of my calcium?
Double the calcium concentration.
Double? So if I have 0.100 molar, then I need 0.200 molar. Is that correct? Okay. So let's say how much chloride would be required to precipitate 100% of my calcium 2 plus. And so the answer, 0.200 molar. That should precipitate all of it, right?
Can I be 0.5? I mean, 0.05?
0.05? You're thinking S.
Well,
Really? Well, let's try it. Let's see what happened. And so, let me go back and see if I have the. Do you see this? This is my KSP value right here. 3.9 times 10 to the minus 11. I'll just use that. That might be different than the books, but I don't want to look it up in the book right now. So let's set up this problem. So I got calcium fluoride solid. This is going to calcium 2 plus 2 fluorides. This is 0.100 molar. This is 0.200 molar. You know what we're going to do? We're just going to try it and see what happens, right? And so this is my initial. KSP is equal to 3.9 times 10 to the minus 11, which is equal to the calcium 2 plus times the fluoride squared. And so what's the change going to be? Is the change going to be complete? Going backwards? Is that very large, or could you call this very small? And yeah, going backwards. It is very big going backwards, but is that very large? Very, very large? Very, very, very large? What is it? Well, we got a number here. If we got a number here, over there, do we have any numbers? No. If we got a number, we could calculate it. We don't have to do that. We just go minus S or minus X? Minus X. Minus 2X. This is not solubility here, right? Because we're precipitating out. And so we're going to get 0.100 minus X, 0.200 minus 2X. Molar. Is this the way you would have done it? Yeah, okay, we'll do it. We'll finish it. Keith, do you have a question?
Is the question how much water would be required to dissolve out 100% calcium fluoride or calcium 2+?
Calcium 2+.
How can you precipitate calcium 2+?
With fluoride? How did you precipitate calcium 2+ in your unknown? With oxalate?
Like dissolve it? Isn't it precipitate with dissolve it?
I'm sorry? Yeah, we're just, how does it precipitate? 0.200 molar? Well, let me finish this problem and then we'll talk about that. 0.100 minus X, 0.200 minus 2X gives us squared, gives us this. It's going to be, what is it going to be? Oh yeah, you know, this is going to be what, a cubic equation? We could get it in cubic form and use our calculator, right? Or we could try to reset. Do you guys remember resetting? Yeah. In fact, I would have reset this because look at this. Which side is favored? The left side. And so we should have reset it. I shouldn't have even gone this far. I should have just reset it immediately. Right? Shouldn't I have? Yeah. I should have reset it. And so let's go ahead and reset it. If I reset it, what does it reset to? 0, 0. Is there something wrong with that? Or is that okay? That's okay. It's like if I had 100 gallons of water on the left side and I push all that to the right side, then, oops, no, I'm sorry. If I have 100 gallons on the right side and I push it all to the left side, then I have 0 gallons on the right side, right? But that 100 gallons is still over here. So I didn't destroy any atoms. They're still there, right? All right, then the change is going to be plus S or plus X? Plus S. And plus 2S. And so at equilibrium, I'm going to have S molar and 2S molar. And so here, this is just going to be S times 2S. Wow, what a difference in math. Just by resetting it, look at how much easier it is to solve. And so in this chapter, what do you think you're going to be doing a lot of? Resetting. This is going to be 4S cubed, and S is equal to actually, does somebody have a calculator? 3.9 times 10 minus 11 divided by 4. Take the cube root of that. .13 times 10 to the negative, shoot. You know what that means? That means that, did I precipitate it out, all my calcium?
No.
No. Surprisingly, 0.200 didn't precipitate out all my calcium because there's still some calcium left over, right? 0.2 of a millimole of calcium per liter left over in solution at equilibrium. And so 0.200 wasn't enough. 0.200 molar fluoride, not enough. Huh. What should I try next? Maybe double it. Let's try to double it, and that should precipitate it all out, right? Should I try 0.400?
No, because resetting it gives us the same.
Should I try? No, it doesn't. No, it doesn't. 0.400 will be better. Let's do it. You want to try? Let's try it. Because I had, how much calcium did I have? 0.100. Now I'm going to try 0.400, twice as much, right? As I should need. Now when I reset it, right, automatically I want to reset this because look at that K. And so I reset, and then my new initial will be what? 0 molar and 0.200 molar. So this is going to be minus, I'll call it Y minus 2Y. Remember? Yeah. And then we're going to be doing better, right? This should be better because common ion effect. I mean, we're gonna maybe. And so what's the change going to be here? Plus S plus 2S. And so at equilibrium, I'm just going to have S molar and 0.200 plus 2S molar. And then let's plug that into the KSP equation, which is going to be S times 0.200 plus 2S squared. Should I try the simplifying assumption here? What do you think? Yeah, let's go ahead and try it. You know, would the simplifying assumption work well in the reverse direction? No, it's awful in the reverse direction. But in the forward direction, it should work pretty well because KSP is very small. And so we try the simplifying assumption. This is going to be S times 0.200 squared, which means that S is equal to 9.75 times 10 to the negative 10 molar. Oh, getting better. Actually, you know, the percent change is, this is 10 to the minus 1, 10 to the minus 10. This is about a 10 to the minus 9% change, right? Something about that. 10 to the minus 8, 10 to the minus 9, 10 to the minus 10%. So the simplifying assumption was perfectly valid. In fact, if you did the quadratic, you'd probably get this exact same number. But did we precipitate it out 100% of it? No, because you know what? There's still a little bit left. 9.75 times 10 minus 10 molar. I want to get all of it out. And so what should I try next? .400 wasn't enough. Maybe I should go to 40 moles of fluoride per liter. You think that'll do it? Yeah, I could try 40, but you know what? 40 molar fluoride is not enough. Do you think I can get 40 moles of fluoride in a liter? Probably not. But I could try 400,000 molar. 400,000 molar, will it do it? No. In fact, you should be able to see this. What molarity fluoride do I need? Infinite. So I need infinite molar fluoride to precipitate 100% of the calcium. What does this tell you? It tells you that it's impossible. It's impossible to precipitate out 100% of the calcium. It's, you know, in practical terms.
Is 100% 0.1 molar? Or what?
Yeah, all 0.1 molar. I don't want anything left. If you have
So shouldn't you decrease the concentration of fluoride if you keep increasing it more as you keep getting smaller and smaller and smaller?
well, we did. We decreased it down to 0. Remember, the previous problem had it all the way to 0, the fluoride. And the soluble is actually quite a bit higher, 10 to the minus 4 molar. So it didn't work. And so, yeah, think about it. But basically, what this tells you is that in all your precipitations that you did in the qual, none of them were 100%. Even if you added a whole bunch of extra precipitating agent, none of them were 100%. In fact, it's impossible. Well, if it's impossible, then should we just give up? No. But we don't give up. You know what we say? Because what's going to happen, although this is nonlinear, but I mean, we're like something like S squared. What's going to happen is, you know, we'll rapidly precipitate it, and then what's going to happen eventually is it's going to just approach 0, you know, asymptotically, and then hit it at infinity, right? And so what we can say is that so little remains that it's kind of negligible. You know, if you see this, you know, 10 to the minus 10 molar remains, that's almost like nothing. If you made let me ask you this. If you made a 10 to the minus 10 molar HCl solution, would you drink it if it were just pure water and HCl? 10 to the minus 10 molar, yeah, no problem, because that's better than probably the water you're drinking currently. The water you're drinking currently is probably a heck of a lot more acidic than that. You know, and sodium chloride is the most common ion in water. And so, in other words, we're going to hit a point where we're going to say that's enough. That's pretty good. We got practically all of it out, and the only bit that remains is negligible, right? And so what do we call that point? What we call that point is, so when we're doing precipitations, we look at the percent precipitation. We must consider the percent precipitation. And so let's do this one first. The way we calculate the percent precipitation is first calculate the percent remaining. And so this is the concentration at equilibrium. That's over the concentration initial. This initial is tricky because we have two initials. Which initial should we use? You know, if we're looking at the percent remaining, then should we use the reset initial or should we use the initial initial? We got to use the initial initial. We can't use the reset. And so we'll call this the initial initial, not reset. Times 100%. And so the amount that remains at equilibrium is 9.75 times 10 to the minus 10 molar calcium 2 plus. That's how much we have left over from our initial 0.100 molar calcium 2 plus times 100%, which means we precipitated out what percent of our calcium ion at this point?
9.75 times 10 to the minus 11.
Oh, okay, sorry, we didn't precipitate out. This is 9.75 times 10 to the minus 11 molar remaining. If that's the amount remaining, how much did we precipitate out? Well, the amount that we precipitated out is just a simple calculation because it would be 100 minus the percent remaining would be the percent precipitated. And so it's just 100% minus the percent remaining equals the percent precipitated. Okay. And so we'll do this. It's going to be 100 minus this. 100 minus 0. How many zeros do I need? 10 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 9, 7, 5. This is going to be 100.00000000000.
Is that should be 10 to the negative 9? 10 to 100%. 10 to the negative 9.
Oh. All right. Okay, I thought that was 10 to the negative 9 molar. Okay. I need to redo this. So I need 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 7, 5. Which means this is going to be 99.999999025.
Are you subtracting the percent remaining?
Yes.
In that case, we didn't multiply it by 100%. It would be the negative 1, or, yeah, negative 1. You only divided by the 100.
Actually, okay, 10 to the minus 11 times 10 squared should be 10 to the minus 9. I got my units wrong. Sorry, this should be percent
Okay.
remaining. So if that's the percent remaining, this is the percent that was precipitated. The reason I usually do the percent remaining calculation and then calculate the percent precipitation is because of round off error. If you were to calculate the percent precipitation directly, this would just round off to 100 in your calculator, right? Or would it? I don't know. Actually, should we try it? I'm just curious if it would round off.
No, it's like 99.999.
It does?
Yeah, but it stops at a 9 because it's like 0.
All right. Maybe, let's see, 99. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 nines. Do it this way. Actually, I'm curious because I haven't done it in a while, so I'm just curious. Let's do a side check. Or calculate percent precipitation directly. How would we calculate the percent precipitation directly? The way we calculate the percent precipitation directly is to figure out the molarity precipitated. Now that's kind of weird because usually we figure out the moles or the grams precipitated, but in this case we're going to figure out the molarity precipitated, which is unusual a little bit. The molarity precipitated is 0.100 molar initial minus the amount that remains. What is the molarity that remains? The molarity that remains is 0.00. Now I need 9 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 zeros and then a 9, 7, 5. And so I had 0.100 molar to start, and then I lose this much molar that remains, and the rest was precipitated. Does that make sense? And so this is going to give us, can you do this in your calculator? Well, it's going to come out to 0.09999999925 molar, right? That's how many moles per liter we lost. Now, to calculate the percent precipitated, we just do this. The percent precipitated is equal to the molarity precipitated over the initial molarity. And so the molarity precipitated will be 0.09. You save this in your calculator, right? 999 dot 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 over 0.100 times 100%. And so do that calculation in your calculator and see what it comes out to. It's this, actually, how many nines do I need? 6 nines after this, and then a 025. What does it come out to?
Like 99999999025. Oh wait, sorry, there's multiply by 99.9.
All right. Didn't round off. We're okay. No. We're okay. But are you always going to be okay? No, you aren't. And so you got to be prepared for that time where your calculator might round off and then do it a different way. Even on anyway, it's 99.999999025% precipitation. What do you think? Is that close enough? That's pretty good, right? Where do you want to draw the cutoff? Where would you say, you know, that's good enough? We've gotten practically all of it. 4 nines? 4 nines? 4 nines sounds pretty good. You know, 99.99. Maybe 5 nines, 6 nines, 3 nines. You know what your book is going to say? 11 nines. Your book is going to say 3 nines is adequate. And so the book says 99.9% greater than or equal to 99.9% is called a complete precipitation. And so for the most part, we completely precipitated it up. Even though, you know, it's impossible to completely precipitate it up, but it's good enough, right? And so that was with 0.400. With 0.200, did we get complete precipitation? Can you calculate it? With 0.200 molar fluoride, was the precipitation complete? Go ahead and calculate it and see.
I got 99.78.
99.78. 99.78%. If this calculation is correct, then would we call it a complete? Did we get it? No. Not enough. Not enough for a complete precipitation. And so complete precipitation is somewhat arbitrary, you know, just some number. It's close enough. Oh, are we okay with this then? So this gives us some control over things. And so the next thing we're going to talk about is something called a fractional precipitation. A fractional precipitation is a separation technique. which we did in lab, actually. We did a fractional precipitation in lab, and the fractional precipitation in lab that we did was to separate the 3+ cations from the 2+ cations. How did we do that? How did we separate the 3+ cations from the 2+ cations? Yeah, and using what? Using, yeah, right. And so let's do this here. Let's put in 2 cations here to keep it simple. Let's put a 2+ cation. What 2+ cation do you want to use?
Iron.
You had magnesium. You didn't have iron. You had 3 as 3+. We could use iron as a 3+. You want to do that? So we'll put iron as a 3+ here. And then what 2+? Calcium or magnesium? Magnesium? Which one? Zinc? Magnesium, zinc, or calcium? Which one?
Zinc.
Zinc? All right. Zinc is a little bit difficult because other reactions occur rather than a simple metathesis. You know, because you could get the tetrahydroxozincate ion, which is going to complicate this. And so there are other controls that we do to prevent that from happening. Whereas calcium and magnesium don't. This is why. So let's avoid zinc for right now. Let's do calcium or magnesium.
Calcium.
Calcium. All right, let's do calcium. So let's say I have 0.100 molar, iron 3+, 0.100 molar, calcium 2+. I like 0.100 molar because you can easily calculate percentages in your head. Usually. And we want to separate out the iron from the calcium. And we could do that by doing what we call a fractional precipitation using hydroxide. And so the way it's going to work is this. We add hydroxide. We increase the concentration of hydroxide until one of these start precipitating. Now the question is, do they both start precipitating at the same time? Or do they precipitate at different? Right? And why would they precipitate at different, times? Yeah, the one that's most insoluble will precipitate out first. So qualitatively, the most insoluble one precipitates first. And so which one is more insoluble? FeOH3 or Ca? Oh, actually, calcium's not a good one. Unless we have the KSP. Let me see. Calcium hydroxide is fairly soluble. So let's see if I have the KSP for calcium hydroxide. Eventually, calcium hydroxide isn't going to precipitate. This separation is easy because calcium hydroxide is pretty soluble, and iron isn't. So this is like, how would you separate sand from salt? Just dissolve the salt in water, leave the sand, right? Kind of thing. And so, I'm sorry, let me change this to magnesium. Magnesium is fairly insoluble. And so let's take a look. Magnesium hydroxide versus iron 3 hydroxide. Which one do you predict to be less soluble? Iron 3 because of the charge. And so less soluble one precipitates first. And so as we add the hydroxide, then what happens is this. What happens is the iron starts to precipitate. But the magnesium stays in solution. And so what we'll do is we'll increase the hydroxide. As we increase the hydroxide, we decrease the magnesium. Not magnesium, sorry, iron. Until we hit a point, you know. And these points are, well, there are different ways of thinking about it. But when we start precipitating the iron, that means we've saturated the solution with respect to iron. Fe3+. But it's unsaturated with respect to magnesium. But eventually we're going to have so much hydroxide that it's going to be saturated in terms of magnesium, and both will begin to precipitate out. And so we just generate more precipitate here. And eventually what happens is it becomes saturated with respect to both. Saturated with respect to both. And both precipitate with increasing hydroxide. And so here's where we have to stop. We have to stop here, otherwise we precipitate both. So we do two calculations here. The first thing we calculate is the hydroxide concentration required for precipitation. The hydroxide ion concentration required for precipitation of iron 3+ can be given like this. If the, remember Q? You guys remember Q? QC, QP? The concentrations, the given concentrations. Okay? If QSP is greater than KSP, we expect precipitation. Too much product. If QSP is equal to KSP, that's what we call saturation. It's right on the cusp of precipitation. If QSP is less than KSP, then what we have is we have an unsaturated solution. Nothing should precipitate. And so in other words, when we're down at these low concentrations, QSP is less than KSP. QSP is less than KSP, and then we hit this. We increase the hydroxide so that QSP is now equal to KSP. And if we further increase the hydroxide, then QSP is going to be greater than KSP, and we get precipitation occur.
What is the QSP again?
QSP is the given concentrations. KSP is the equilibrium concentration. So are your given concentrations already at equilibrium? Are they? No, right now, no, because there's no hydroxide. Only the hydroxide from water. So we do this. So we want the KSP to be less than or equal to the iron 3+ and the hydroxide concentration Q. Is actually I should write the KSP equation. The KSP equation is FeOH3 solid goes to Fe3+ plus 3 hydroxide. So if these concentrations are equal, then it's saturated. If these concentrations exceed KSP, then we're going to get precipitation. Correct? And so these are the given concentrations. And so that means, what is the hydroxide ion concentration required for saturation? Okay, the hydroxide ion concentration that's required has got to be greater than or equal to, okay, it's going to be the KSP divided by the iron 3 plus, and we'll take the cube root of that. Thank you. So this is 4 times 10 to the negative 38 divided by the iron 3 plus, which was what again? 0.100. Taking the cube root of that, which means the hydroxide's got to be greater than or equal to it's going to be a very small number. To the negative 13 molar, which means the POH is equal to what? The negative log of that. Twelve point one three. One more digit.
2.
2. Which means the pH is equal to 1.8, 67, 68, 67, something like that. What's weird about this? Is there something that's weird? I'll tell you, there is something that's weird about this. What's weird about this? It's super acidic. How the heck are we going to precipitate out a hydroxide in a... That's a very acidic solution. Hydroxide is base. How are we going to precipitate out iron 3 hydroxide in this highly acidic solution? Did we make an error in our calculation? Don't we need base to precipitate? Don't you need ammonia or something like that to precipitate out the hydroxide, iron 3 hydroxide?
Is the pH?
It's not. It's the remaining.
The remaining hydroxide is this minuscule amount of hydroxide?
Is the pH not assumed to be 7? So should it be 7 plus 1.86?
Oh, that's right. We didn't, you know what? Maybe we didn't consider water, huh? KW. Oh, yeah, you're right. Maybe the pH isn't this low. But you know what? We are considering water because this is hydroxide from anywhere, right? Water and whatever else. That's a total hydroxide, which includes the hydroxide from all sources.
Is the hydroxide in the remaining solution, not those hydroxide precipitated out?
No, this is not the hydroxide in the remaining solution, is it? Oh, you're right. It is. It is the hydroxide in the remaining solution. Because the initial hydroxide should be a little bit higher. Why? The initial hydroxide should be a little bit higher because we're consuming some of it for precipitation. And so if we do that, then this is what we get. We have some initial hydroxide here, and we have this 0.100 molar here, and then there's going to be a change in equilibrium. And so at equilibrium, I know what I have here. the hydroxide concentration at equilibrium, assuming it's saturated, is going to be 7.36 times 10 to the minus 13. And over here, this is going to be one-third of it. And so 7.36 times 10 to the minus 13 divided by 3. This is one-third the concentration of that. Does that make sense? And so we did have to add more hydroxide, but this is still weird because even if we had to add more hydroxide, the amount of hydroxide that we added, well, actually, I guess we could figure it out, would be this. This is going to be minus x minus 3x, where x is this, right? No, x isn't that. Where x is 0.100 minus this. And so it's going to be, well, let's figure out what x is. X is equal to 0.100 minus this. So if somebody can punch this out, that would be good. So it's just a whole bunch of zeros. And so this is going to come out to 0.099999, or about 0.100, right? And so that plus this is going to give us around 0.100 molar initial hydroxide. And so this solution would have had to been about 0.100 molar initial hydroxide. Right?
300?
Yeah. But do you see how come people call this chapter pretty tough? Because do you know what I just did? I kind of wasted a lot of time. I wasted a lot of time because it's so easy to get mixed up. Because you know what? Nothing's precipitated yet. What is my iron 3 concentration? What is my iron 3 concentration at equilibrium? Or whatever. What is my iron 3? 0.100. Did I lose any of it?
No.
No. I haven't lost any of my iron. In fact, I haven't even precipitated anything because what we're doing is we're taking it from unsaturated just to saturated. This is the minimum amount of hydroxide I need to start precipitating. We do this calculation all the time, because we got to figure out what the initial is. But you know what? This is wrong because I still have 0.100 molar here. Do you see? I haven't precipitated one bit of it yet. I just want to figure out at what point is the hydroxide going to be saturated. And so this is, well, fortunately, this is the last and the hardest of the equilibrium chapters, right? And so it's the last, so it doesn't get harder than this, which is good, right? But this is harder than what you've already been doing because there's more variability in the calculation, so you have to be careful. Otherwise, you could easily do this. We haven't precipitated one bit of it yet. And so this hydroxide is actually the hydroxide, and it's weird because it's so acidic. And so the answer that I was looking for is this. If you look at that KSP, this KSP is crazy small, which means that iron 3 hydroxide is incredibly insoluble. It's so insoluble that you only need a tiny fraction of the hydroxide generated by water collisions. You know, in pure water, you can generate 10 to the minus 7 molar hydroxide. You don't even need that. You know, you could have acid in there and generate even less hydroxide and get iron 3 to precipitate, which is amazing. You know, that's how insoluble this stuff is. Well, we ran out of time, so we'll talk more. But this chapter, be prepared for some challenge in some of the problems. Okay, setting it up and figuring out what's going on.
Yeah.